Okay, in this video, we're going to look at how to use the second derivative test to identify whether a function has a maximum or a minimum value, or perhaps neither, at critical points. There's only 3 steps involved, so the second derivative test is fairly easy to use, and we'll run through these steps in a second. Now, if you haven't done it yet, this is actually part 4 of the video series on the second derivative. And if you haven't done it for sure, I'll go ahead and watch the first 3 videos, but definitely watch the first video because it will make the stuff in this video make a lot more sense. Now, you might say initially well, in a previous video, didn't we use the first derivative test to identify where you have maximums and minimums? And that is true. So what the second derivative test is, it's just another way of identifying maximums and minimums. But in a way, the first derivative test and the second derivative test give you the same information. Now, I think this will make a little bit more sense if we, first of all, let's back up and take a look at what the first derivative test looks like and what it has to say. And it's laid out fairly similar to this one. So here's what the first derivative test says. Now, here's the first derivative test. And it says this: at a critical point, if the first derivative changes from positive to negative, you have a relative maximum. In other words, if it goes from increasing to decreasing, you had to have a relative maximum at that point. If the first derivative changed from negative to positive, in other words, it went from decreasing to increasing, then you had to have a relative minimum there. And then finally, if the first derivative does not change signs, suppose it went from decreasing to decreasing again, then you had neither a relative minimum or a relative maximum. This is going to make a lot more sense if we look at a graph. So let's first of all go to look at a graphical example of this before we actually work out a numerical example. Now what I'm going to do is, here is an original function. What we'll do is we'll put the original function here, we'll put the first derivative graph here, put the second derivative graph down here, and see how they all tie together. But before we get started, I'm just going to go, and if you have the graph, you can just look at it. You can tell whether you have a relative minimums or maximums, so let's go ahead and put those on there. So on this blue graph, what I'll do is I've got a horizontal tangent right here, so I'll go ahead and put that on. There's a horizontal tangent. Now what that means is that is a critical point because the first derivative is equal to 0. And clearly you can look at the graph and tell that that is a minimum. So we'll just go ahead and put these on here. Here is a horizontal tangent that says this is a critical point, and in this case, clearly this one is a maximum. I've got another horizontal tangent right here, so that is a critical point. But in this case, it went from decreasing to decreasing again. You can look at it and tell clearly that is neither. It's not a relative minimum or a relative maximum. Another horizontal tangent right there, that's a critical point. And clearly that is a minimum. And then finally, horizontal tangent up here, that's a critical point, and clearly that one is a maximum. So if you have the graph, it's very easy to tell where you have minimums or maximums. So now let's take a look at the first derivative graph and see how the first derivative test will identify these for you. So let's go ahead and just put the first derivative graph on here. So this would be the first derivative graph. Now, as far as the rules go, we'll go back to those in a second. Let's go back and take a quick look at them. So here is the first derivative test. And what it says is this: if the first derivative changes from positive to negative at a critical point, then you have a relative maximum. So let's look at an example of that. So what happens is, looking down here, the first derivative changed from positive to negative at a critical point. Now on this black graph, wherever the first derivative graph goes through 0, then you have a critical point. So each one of these black dots here is a critical point. Well, the first derivative went from positive to negative at a critical point, and sure enough, you have a maximum up here. Then let's look at the next possibility. The next one says this: if the first derivative changes from negative to positive at a critical point, then you have a relative minimum. So let's look at that. So if it goes from negative to positive at a critical point, then you have a relative minimum, which is what you've got up here. And the same thing applies over here. It went from negative to positive at a critical point. You've got a relative minimum right here. So back to the rules again. So that's what the first two say. Now the third one says this: If the first derivative does not change signs at a critical point, then you have neither a relative minimum or a relative maximum there. Let's look at that example. And that would be this case right here. So what happens is the first derivative was negative, hit a critical point, and it stayed negative again. So it didn't change signs. In other words, it was decreasing, leveled off just for a second, went to decreasing again, but clearly you have neither a relative minimum or a relative maximum right there. So that's how the first derivative graph will help you identify intervals where it's increasing or decreasing. You might also notice anytime the original graph goes from increasing to decreasing, then you'll have a relative maximum. If it goes from decreasing to increasing, you'll have a relative minimum. And again, that fits in with these rules, and those are the rules for the first derivative test. Now, the second derivative test will also help you identify minimums and maximums, so let's look at those rules. So here are the second derivative test rules. And what the second derivative test says is this. If you have a critical point where the first derivative is equal to 0, in other words, it has a horizontal tangent, then the following is true. If the second derivative is positive at that critical point, in other words, if the graph of the second derivative is above the x-axis, then you have a relative minimum at that critical point. Now let's look at that case. So we'll go back to here. And let's first of all put the second derivative graph on there. So I'm going to add, here's what the second derivative graph would look like for this function. And just to keep things from getting a little bit confusing, we'll go ahead and let's turn off this first derivative graph. And here's what the situation looks like. So the rule says again, if the second derivative is positive at a critical point, then the original function has a relative minimum at that point. And here's what that means. So here is a critical point right here. So we've got a critical point here, comes straight down from there. The graph of the second derivative is positive. It's above the x-axis, which guarantees that you have a relative minimum right there. Let's take a look at this one. Here is a critical point. Let's come straight down from there. The graph of the second derivative is positive, which guarantees that you have a relative minimum. So at a critical point, if the second derivative graph is above the x-axis, if it's positive, you're guaranteed to have a relative minimum. So that's the first condition. Now let's take a look at the second condition. At a critical point, if the second derivative is negative, in other words, if the graph is below the x-axis, you're guaranteed to have a relative maximum there. So let's look at that one. So here is a relative maximum at a critical point. If you come straight down from that point to right here, the graph of the second derivative is negative. It's below the x-axis at that point. So if the graph of the second derivative is negative at a critical point, then you're guaranteed to have a maximum there. Here's another case of it over here. Here's a critical point, comes straight down from there. At that point, the graph of the second derivative is negative. It's below the x-axis, which guarantees that you have a maximum at that point. So that's the second condition. Okay, now let's look at the final condition. What happens if the second derivative should turn out to be equal to 0 at a critical point? If that's the case, then the test fails and there's no guarantee that you have a maximum or a minimum, and it could be neither. So let's look at that case. So what happens is, here's a case where it's neither. So at a critical point, if you come straight down from there, the graph of the second derivative hits the x-axis, it's equal to 0. And what that tells you is that the second derivative test fails and the original function, in this case, has neither a minimum or a maximum. So again, if the second derivative is above the x-axis at a critical point, you're guaranteed to have a minimum. If the second derivative is below the x-axis at a critical point, or negative, you're guaranteed to have a maximum. And then finally, at a critical point, if the second derivative is equal to 0, you're guaranteed to have neither. So that's what the rules look like. So now that we've got the rules in mind, let's go and we'll try an example here. So again, what we'll do is we want to find, given a function, we want to use the second derivative test to find out whether the function has a maximum or minimum values, or perhaps neither, at the critical points. So now let's look at a specific example. Okay, and the example looks like this. What we've got is the original function is f of x is equal to minus 3x to the fifth, 5x cubed. Now, your approach is going to be to do this. First of all, find the first derivative and use the first derivative to find the critical points. Then you'll need the second derivative. Evaluate the second derivative at the critical points and find out if it's positive or negative or neither, or zero, which will tell you whether you have maximums or minimums or not. So let's go ahead and we'll run through the steps and see what we got here. So I'll put step number 1 here, and the very first step is to find the first derivative. Find f prime. So you're going to need the first derivative because you need to know where the critical points are. So in this case, f prime of x, the first derivative, and we'll just use the power rule on this. This would be, bring the 5 down, this would be minus 15 times x to the 4th power plus 15 x squared. So there's the first step, find the first derivative. Now the second step is you need to find the critical points. So you want to find the CPs, the critical points where the first derivative is equal to 0. So we want to find first derivative where it's equal to 0. So take the first derivative, set it equal to 0, and solve for x. So what that's going to give me would be minus 15x to the 4th plus 15x squared, and set that function equal to 0. Now go ahead and factor it. You can factor out, in this case, you can factor out a negative 15x squared, which is going to leave you with an x squared. In this case, you'd have an x squared right here, minus, and this is going to be a 1 right here. So it leaves you with an x squared minus 1. Now, this one will actually factor one more time. I'll factor it into this. 15x squared, and this will factor into an x plus 1 times an x minus 1 is equal to 0. Now to solve this, set each factor equal to 0. Set that one equal to 0, set that one equal to 0, and set that one equal to 0. What this one's going to give you is x is equal to 0. There's one critical point. This would be x plus 1 is equal to 0, which gives you x is equal to a negative 1. There's another critical point. And finally, this last one, x minus 1 is equal to 0, or x is equal to 1, and that will give you a third critical point. So there are your CPs, your critical points. We'll go ahead and plot these on the axis. So what you'll have here is you've got a critical point right here, you've got a critical point right here, and you've got a critical point right here. Now, what that tells you, at the critical points, you know you have a horizontal tangent, but let's look at some possibilities here. So one possibility is maybe the horizontal tangent is down here and you have a local minimum. Maybe the critical point, you have a horizontal tangent up here and the graph has a local maximum up here. And then finally, the last possibility, maybe it comes down like this, levels off just for a second, and you have neither. So you know you have a horizontal tangent at these critical points, but you don't know whether they're maximums or minimums. So to find that out, we now need to find the second derivative. So we'll go down and we'll call this step 3 right here. So in we'll put it right here, step 3 is, now step 1 was find the first derivative. Step 2 was use the first derivative to find the critical points, and I know where your critical points are. And what step 3 is going to be find, you're going to need the second derivative. So go ahead and find f prime prime. So what the second derivative would be, so f prime prime of x, it's just going to be the derivative of the first derivative. So what this will turn out to be would be minus 60 x cubed, we'll just use the power rule on this, and then bring the 2 down, plus 30x. So this is the second derivative. And you're ready for the last step. Now, what the second derivative test says is, let's just go back to that. The second derivative test says is this, as evaluate the second derivative at the critical points to see whether you have relative minimum maximums or it fails. So when you evaluate the second derivative, you go ahead and plug each one of your critical points in. If it's positive, you have a minimum. If it's negative, you have a maximum. If it's equal to 0, then the test fails. So let's go ahead and try that. So this will be the fourth and final step on this. So what we'll do is go over here to step 4. And step 4 says evaluate the first or second derivative at the critical points. So I'll evaluate the second derivative, f prime prime, at the first critical point. Then evaluate the second derivative at the second critical point. And then finally evaluate it at the third critical point. So plug the critical points into the second derivative and see what the sign is. So in this first one, it'll be negative 60, and I'll plug in a negative 1 plus 30 times a negative 1. And when you do that, this will turn out to actually be a positive 30. But again, all I'm interested in here is positive. It'll turn out to be positive. And the fact that the second derivative is positive, let's go back to the rules. So if the second derivative turns out to be positive, then you have a relative max or minimum at that point. So this tells me that I have a relative minimum at x equals negative 1. Now let's find out what's going on at 0. So I'll plug a 0 in. So negative 60 times 0 cubed plus 30 times 0. Now, since both those terms are 0, this will turn out to be equal to 0. So what does that mean? Well, let's go back to the rules. The rules say if the second derivative is equal to 0 at a critical point, then the test fails and you have neither a minimum or a maximum here, or possibly neither. And in this case, you'll see it'll turn out to be neither. You don't have a minimum or a maximum. So in this case, the test fails. So the test fails. So I have neither a minimum or a maximum there. So in this case, the second derivative of the test failed. Now let's look at the third possibility. So at the third critical point, negative 60, plug in a 1 cubed plus 30 times 1. And if you evaluate this one, the answer will actually turn out to be a negative 30. But again, all we're interested in is the fact that it is negative. Now, what does that mean? Well, we'll go back and look at the rules. So if the second derivative turns out to be negative, that tells you that you have a relative maximum at that point. So this means that you have a maximum at x is equal to 1. Now, really, if you're doing all this, the actual answer to the questions would be this right here. You've identified whether you have maximums, minimums, and so on, so it'll actually look like this. So there is the actual answer to the question. Now, finally, on this last one, we could actually do this. The test failed at x is equal to 0. So at the first critical point, you have a minimum. Second critical point, the test failed. Third critical point, you have a maximum. Now, again, you don't have to do this, but if you sketch a quick sketch of this thing, you'll see why all these things make sense. Let's just go ahead and put the graph on here. So if we added the graph to this, here's what the graph would look like. And what it tells you is this, is that at the first critical point, you have a minimum, and sure enough, you have a horizontal tangent right here. It's a critical point, and f prime is equal to 0, and that was a minimum. That's the second one. The test failed. You had a horizontal tangent there, So f prime was equal to 0, first derivative was equal to 0, but again, you have neither a relative maximum or a relative minimum there. So it looks like that. Neither. And then finally, the last possibility, at the third critical point, you had a horizontal tangent right there. So that, again, is where f prime is equal to 0, and that was a relative maximum. So that's what the second derivative test says. So let's go back and take one last quick look at the rules. So if the second derivative is positive at a critical point, you have a relative minimum. That would be this case right here. Second derivative is positive, you have a minimum. If the second derivative is negative at a critical point, you have a relative maximum. That would be this case over here. So second derivative is negative, you've got a relative maximum. In the third possibility, if the second derivative is equal to 0, then the test fails and you have neither a maximum or a minimum, and that's what happened right here. So there's an example of how to use the second derivative test, and really it's very easy to do. Just find the first derivative and use the first derivative to find the critical points. Then you'll need the second derivative. Evaluate the second derivative at the critical points. I think I'll actually go ahead and write that in there. So step number 4 is to evaluate f prime prime at the CPs, at the critical points. So that would be step number 4. And then again, if it turns out to be positive, negative, or 0, you'll know whether you have a relative minimum or a maximum, or perhaps neither there. So there's another second derivative example.